Okay. So this is a talk I upgraded from Iowa earlier this last month. So that's the upgrade. It's a general kind of. There are actually 3 talks in Iowa. I only managed to cover this part. It has a general title, quantum oscillations, and it involves oscillations in many quantum systems. Last week we had a talk on the Majorana fermions by Poliana. That's kind of a hotish topic, and we have done some work on that. And if you have any interest, we can talk about this. Maybe tomorrow is a good day since we have a kind of free afternoon in a way for discussions. There are also Shubnikov-de-Haas oscillations. That's work. It's actually quite a nice piece of work in which we generalize. For those of you who've heard of a persistent spin helix, mostly, this kind of spin density wave, except that it's not a spin density wave because it's non-interacting, and it's an excitation, not the ground state property. We found a new sweet spot, as we call it, for reach. We have not only alpha and beta. Alpha is the Rajba coefficient. Beta is the Dressel-Haus coefficient. These 2 types of spin orbit interactions in semiconductors like indium arsenide or even gallium arsenide. And a couple of years ago, people showed. Actually, it was on work we've done back when I was in Basel, more than 20 years ago, with John Schlim and Daniel Voss. And then Andre Bernweg and others, Zhang Zhang and Taylor Hughes, they coined the name and they extended it, and that it was a nice extension. So now we found another condition which shows up in the usual beatings of the Shubnikov-de-Haas oscillation. Usually you have Shubnikov-de-Haas oscillation, you have beatings, and this is a signature of the Rajba, or the spin orbit interaction. You see 2 peaks. And this is a system that we can have both Rajba, Dressel-Haus, and also the G factor being non-zero. And at this sweet spot, the beatings vanish, and they vanish in all harmonics of the Shubnikov-de-Haas oscillation. So I can have a full talk on that, and if you're interested in this kind of thing, we can discuss. Today I'm going to actually try to focus on this, because this is the, I think, the novelty. This was a work I was involved with when I was in Basel for my sabbatical, and it involves a whole qubit. It doesn't really matter. That's the point that I'm going to try to make is you have a 2-level system, and you can transverse drive it, and at the same time longitudinally drive it with omega z. This would be, as you see, at the megahertz frequency. This is going to be actually this megahertz, and then the transverse drive is at gigahertz. And under certain conditions, of course, you have, with the usual transverse drive, you're going to have the usual Rabi oscillations, but then we add the longitudinal drive, and we change this chevron, the usual Rabi chevron, and the main peak. Basically, we can tune this, these parameters, the ratio between these 2 frequencies here, and the main peak would disappear, and we'll find side bands. Oops, yeah, okay, so so here's basically, okay, so this you saw before, I believe people remember well the first slide, so I'm already showing you the main thing here. So this, Poliana discussed quite a bit last week, and this is what I mean here. So this is the results I'm going to show. This is a theoretical prediction, and this is the experiment. It was a very neat result that was done very nicely in Basel, and Simon Geyer is the experimentalist, and this is Stefano Bosco, who is now at Delft. There was the prediction, and then Simon and some of the other experimentalists here went into the lab and found that. So I'm going to discuss this. There's also this nice paper which is currently under review, where there are all the details, and this involves it's a different work, and there's a thesis actually written by Miguel Caballido, who's a student of Dominic Zumbel. It's not public available yet. I was actually double checking with him whether I could show the thesis, because they have the copyright things in there in Switzerland, so we're still waiting for that. Anyway, okay, sorry, there's a delay here. So just a brief. I'm going to flash the slide. This is the kind of things I've been doing for the last 10 years or so. So Dennis already showed this kind of system. That was his PhD work. Also, this was part of his PhD work. He's also first author in that one. And there's, these are basically topological insulators. So in this work, he showed that you can find edge states, protected edge states in a trivial quantum dot. There's also, again, we showed this before. We're very proud of this work here. It's like 10 years old, because we're basically outsiders to this field of the Majorana Fermi Majorana bound states. And this is the first time I think it's one of the different ideas in this vast literature, in which you couple the quantum dot to a linear chain, a Kitaev chain, and we showed that there's a Majorana leaking into this dot. So the Majorana basically end up, if you heard a little bit of Majorana, you know that they like being at interfaces or at the end of this. Is basically, a topological excitation that lives on the edge of the system. And the dot, in this sense, the way to think about it is that the dot is basically an additional site to this this system. So even though there's no superconductivity in the dot, the Majorana basically end up there, and it creates a resonance, and you can tunnel through this resonance, even if the dot energy level is, say, far above the energy level, the Fermi level of the leads. So there's no Kondo in this sense. So actually this was part of the deal with this work, that we, at the early days, like 2012, when this first work from the Delft group came out, there were a lot of questions about whether the zero bias peak was in Majorana or not. So this could be Kondo, could be disorder, could be whatever. It's still, if you've been following this, it's still very controversial. And I actually, as I mentioned in the Iowa talk, I went through a lot of that, and there's a lot of back and forth, fighting and comments to comments, and it's kind of funny to see that. And of course, Microsoft is putting all this effort. You've probably seen some of this, the videos, and quite interesting about this not entirely accepted topological qubit as it's being sold. So it's been sold in the paper, in the Nature paper that they published earlier this year. If you were at the March meeting, you probably attended, in the news that they, of course, they have additional measurements concerning the X and Z gate. That still, for some people, some it's convincing. Some of the, I think one of the gates is looks like noise. So there's still a lot of work to be done. Now, there's also, in the context of spin-orbit interaction in gallium arsenide, for instance, this work here, it's collaboration with the group of Dominic Zumbel. The samples are from David Ashlam. lab in Chicago. And basically, we extended it. The idea is quite nice if you're familiar with this PSH. The idea is, so it's possible, as I mentioned before in my first slide, if you tune the spin-orbital interactions, alpha, Rajba, and Dresshaus beta to the same value. That's the work we done 20-something years ago with John Schliemann and also Daniel. At that time, we thought this was just one point, symmetry point, if you want, like a sweet spot. And more recently, in this paper, we actually extended the idea that because the beta here, which is this Dresshaus coefficient, can depend on the two-dimensional electron density of the two bag, you can vary it. And with two gates, with appropriate gates to the system, you can also vary alpha. So you can vary both and still keep them locked into each other. So you're sitting on this symmetry point where alpha is equal to beta, but both are varying, but still keeping the same value. And when you do this, then what happens is that, so you apply this gate. Oops, I'm going backwards always. Yeah. So you can change, in the original paper, when alpha is equal to beta, you end up with the, this persistent spin helix, like one line here, right? But then, if you, and then of course the pitch of this helix is related to the spin-orbital interaction. Now, if you vary alpha and beta and keeping, but keep them locked to each other, what you're basically doing is you're expanding. Maybe up here you can see it more closely, right? More properly. So down there or up there, you have a helix with a given pitch, and here this pitch is larger. So it's basically, it's similar. This is basically what people used to call the data-das transistor, right? So it's basically the same thing, except that it's an excitation in this sense. And then usually when you think of the spin FET, you're talking about transport, right? To inject, exact. Zeke mentioned that in the early days of spintronics, we were very interested in the spin injection. It turns out that now they all moved on to something else. There's also this, since we've heard a lot about skyrmions in this workshop, I'm allowing myself to show this, which is the related work also to this persistent spin helix. It's actually two persistent spin helix orthogonal. So we have a quantum well with two subbands. In the first subband, we manage to have alpha equals beta. In the second subband, we do alpha equals minus beta, and that we show in this paper that it's possible to change the sign of this Rajba coupling, so that you can generate, if you put your Fermi level, say, on the second subband, it's possible to generate spin densities that look like this. And this is basically a skyrmion. We can actually calculate the Chern number and its topological index. So it's non-interacting, right? It's not like in the chiral magnets where you have interaction. That was the main selling point. It was you could generate some kind of a skyrmion structure or texture in a non-interacting setting, ordinary non-interacting semiconductor two-bag with two subbands. That was what we needed. Yeah. So there was a bunch of other things related also with spin orbit, but let me move to my next slide. Oh man, I know it's flipping the wrong way here. Yeah, so these are some of the people involved over the years. I have right now only one student who's about to finish, because I was basically abroad for 2 years in my sabbatical where I did a couple other things, and I sort of reduced my group. But here are some of the people that were involved, and of course Dennis, Michael, and people from Basel, and now Stefano, that's Delft, and so on. So this is a brief outline. I'm going to focus on the second point here, but there are a lot of interesting things here and here, as I mentioned. So this is the this sort of new sweet spot, right? And this is not, I emphasize, it's not the same as the usual PSH condition. I'm gonna come back if I have time. So the spin-orbit interaction is very important. We've been working, I mean, this is from this review here. We've done a lot of work in the early days. My colleague, Smerindo, is sitting back there. So he did this work here early, many years ago. This is where we introduced the notion of two subband spin-orbit coupling, in inter-subband subband coupling, which enables, for instance, the Skyrmion lattice I just showed you, among other things. So there's a couple of, and also, for instance, the spin Hall effect for the two subband system, intrinsic. This again was the days where, the early days of spintronics, where some of you, the older ones like Georg, had very important contributions. Say, if you're old enough, you probably heard of the conductivity mismatch. That's the man who, and that's what, that's what, for instance, discouraged probably Zeke from pursuing, injection from a ferromagnetic layer into a semiconductor, because this huge conductivity mismatch that that Georg showed, it's a limiting factor. So there are many proposals from that back then, like spin filtering. I also worked on that, and I was trying to, at that time, get away from this conductivity mismatch. And what we did back then was to consider a spin-dependent barrier, because then you would, filter instead of, you would not run into this conductivity mismatch. And this turned out to be also a solution that Albert Fett and others came up with by adding a barrier, near the interface between the ferromagnet layer and the semiconductor, because then you would have tunneling, spin-dependent tunneling. So this is something, if you have interest, we can definitely discuss many aspects and some analogies that may happen, in the quantum magnetics. I'm just going to advertise this work because it involves many of my students here, and some people that were actually at that time here at the Institute. Right? This is number 6 here, is Federal University of Rio Grande do Norte. We discussed a couple of this, some of these works when we were here at that time. And this is basically a generalization. If you're in semiconductor, you know that there are, people like Roland Winkler has a nice book discussing all there is to know about the spin-orbit interaction for electrons, holes, and all that. But this is all zinc blende, and there's a huge expression there for effective kind of effective Hamiltonian that would include the Rashba, the SRs, all kinds of things. So we did basically the same thing here for electrons, but for Wurtzite system. And of course, Dennis is also on this paper, and Esmerindo. Someone asked me when I showed this picture last week, I'm not sure who it was, there was a guy in the picture in the hat, and that's Esmerindo. Some of you pointed out that, who is this guy? So, he's here. This was like 20 years ago, in Brasilia. So yeah, that's the Hamiltonian I mentioned. So you can see that the part that comes from the spin-orbit interaction in Wurtzite system, it's kind of big. It's a very interesting Hamiltonian, because we haven't explored it at all. We derived this. We did some simple calculations for the coupling constants. That's all K.P. But also, Dennis and others did the theory of invariance to make sure we have all the terms. So it's a quite complete work if you are interested in this kind of thing. So so this is the point where I'm going to skip to the second part, where I go to, I actually have nice jokes about this. Maybe I should just show this one here, because it is, since Zeke showed something about the movie. So this also, because I was in Iowa, I had to show that. Because this movie was filmed there in this place in Iowa, and then maybe the older ones will remember this, that they had to build a field so that, this ghost would show up to solve some issues in the past. Do you remember this? So it's a nice, it's, of course, it's Kevin Costner there. And then, of course, I made a pun when I was in Iowa. They might run a field. Of course, it's a field of dreams, and you can, like many of the fields that we work on, and you can look at it in a pejorative way or not. I try to take the positive way and think it's a field that you can dream about many things, like topological quantum computing and things like that. Some people say, oh, fantasy land, but it doesn't matter. But most important thing here is that, and I remember sitting on my quantum antibody class when I was a graduate student, and a prof, one of my profs, Daniel Cox, who is now in Irvine. He used to be at Ohio State when John was there. And he said, when he was teaching phase transitions in the antibody classes, and mean field theory, he would say, it's like, if you build it in, it will come. By that he meant, and I think this I'm mostly focused, targeting this on the graduate students, that when you do mean field theory, you have to be able to be smart enough to choose the right order parameter. So if you want to say a ferromagnet, you choose, say, a homogeneous magnetization. So your order parameter has to have the symmetry you want to find. Or if you want to find a helical state, or if you want to find superconductivity, that's what gave Bardeen, Cooper, and Schrieffer the Nobel Prize. They paired up, fermions, CK dagger, CK dagger, which is, in a normal matter would be 0. So, but that was the order parameter. So that was, so if, of course, you manage to choose the right order parameter and you do the mean field, you minimize your equations, and then you find basically the solution you're interested in. If, it may be physical, even it may be realizable, for instance, a polarized state. Now, I'm saying that because I think to some extent, some of these models, and I would strongly recommend, especially the graduate students, to go read the reviews, the referee reports of this recent Nature paper by the Microsoft team. There are like 4. And if I'm not mistaken, I think one of them is even public. The name of the author is public. The other 3 are not. You can read the extensive criticism and points, and you see how the replies are, and then you can judge for yourself. It's quite entertaining how it is. And I think some of the referees also criticize like the overselling and calling it a topological qubit. In that particular paper, it's not a topological qubit. So many of them point this out, and I think they even say something, you test it, you explain this with this particular model that, has Majorana, and then, that has a 0 mode, so that you didn't quite test it with something else. And so this is the idea of, if you're using a model, and of course, if you build it, it will come, right? Because you're basically expecting it. And of course, this is generated by AI, by ChatGPT. And I remember playing with it and trying to really get Majorana's face of, famous picture that we have, say on Wikipedia, right? Most of you have seen this picture, but ChatGPT was unable to put this face. It would give me all kinds. So I just said, come on, you can. Of course, I have long discussions with ChatGPT. My son usually says that I abuse the little thing, and I say, well, he's going to come after you if he ever, develop super intelligence. So at some point, and of course, I'm in Iowa, so and the movie has to do with baseball, so that's why I wanted them to have, ChatGPT to have Mayrana in this outfit. And I said, okay, remove the cap. Maybe you can at least give me the right, hairstyle. But no. And then it changes also the face, so it's completely unrelated. So it's still has problems there. Anyway, so I think the serious part here is really that, like what I just said, like mean field solutions. If you build it in, the parameter by hand, then the corresponding solution will emerge, right? So I think this is, for my point, that you really in this business have to check not only the model that has already, what you expect to see, but rather, test it more broadly. So with that, let me then move to this part here. And of course, I have all this, if you want to see this referees, and we can discuss that. If you have referee reports and things like that, we can definitely discuss it. So let me go back then to this. So it's two-tone because we have two frequencies, one shaking the qubit along this way and the other shaking it transversely. So this is the theme that is in that paper, and when I was there. So it's Posco and Gaia were the main, driving graduates. Posco was postdoc at that time, and Simon was a PhD student. All right, so this is, of course, the system that we consider here as a whole, but so there's a bunch of advantages and disadvantages as well, because it has a strong end-to-end spin-orbit interaction, which is at the same time good and bad. But the main, I think, purpose of this brief talk is just to show you that by driving this qubit in silicon, we can change the response, the Rabi chevron, in a way that is quite general, and maybe it's useful in other fields, like NMR, for instance. So, of course, this was, when I gave this talk, I was talking to graduate students, so the people that didn't have any idea about quantum computing. So many years ago, I wrote this perspective, and it's still quite, for an introduction of what quantum computing is, I think it still has the right words here, in some of the text. Or if you're interested, for the students, you're completely clueless about superconducting. Quantum computing is, you can see that you need superpositions, entanglement, two-qubit entanglement, then your processing is done with unitary evolution of quantum system, and of course you need exchange and so on. So this was a perspective I wrote on this nice paper from Laws from Daniel, and Engel was a former PhD student of him. I do have nicer pictures in this as compared to the main paper. So this basically is a way to measure the parity, and by parity I mean whether the spins are parallel or opposite, by just coupling it to a QPC and basically reading some current that flows through the QPC. So back to the silicon fat. So the idea of this work is basically because it integrates now a qubit into the usual FinFET, and it's a FinFET because of that, and the qubit will be living right here, right? Many of you have been probably swimming in some places where you can maybe even touch like little sharks. So that's the idea, and of course the selling. I mean, this has been studied by the people in Basel, together with guys from IBM. There's a sequence of papers where you can basically apply. So we're looking from this side here. So you have 2 qubits, and you can drive one of them. You can put gates, and you can also rise or lower this barrier. So you can. There are a couple of papers in the group, being prepared and then already published, in which you look at 2 qubit interaction with your by lowering or by varying basically this barrier here. But we're going to focus on just 1 qubit, which is this one here. So we're going to drive it, and because of the spin-orbit interaction, I'm going to briefly go through this spin-orbit interaction. Not exactly this, but some version of it. And for those of you that are not familiar with it, the spin-orbit interaction basically gives you some kind of internal field that has components in principle in any direction. The Rajba, the usual Rajba, is usually lying on the plane. But in general, especially in this kind of system here, which is a whole system, whole qubit, the spin orbit vector has components that are transverse and longitudinal. Say, so what? Well, it's because the spin orbit, unlike in atoms, here or in semiconductors, you can vary its strength by applying a gate. So if you shake your system with a time-dependent gate, somewhere, then your spin orbit field is also time-dependent, and then you can generate things like resonance or Rabi type of resonance in the system. And in this particular case, this can happen both transversely and longitudinally. So this is a 101 crash course on the usual Rabi oscillations. So imagine you have a 2-level system like this. That's your qubit, and then that's the E field and the frequency. So that's the Hamiltonian basically that you end up having. I mean, you can check, say, chapter 4 Cohen-Tanuji, and you'll see this solution there. So you basically have your spin precessing. So there's a magnetic field, and your spin is basically precessing, and then you now apply an additional oscillating magnetic field. That's why the field is going back and forth here. And then you can, under certain conditions, when you vary this magnitude here, you can calculate very easily, actually, the probability that the spin will flip, say, from here up there. And that's given by this formula here. If the driving term is like a cosine or a sine, then you have to actually do some kind of rotating wave approximation, which I'll discuss briefly. But if the oscillating field here is actually rotating, then this problem is exactly solvable. You just go to the rotating frame, and you eliminate completely the time dependence on the system. So you're going to see this in the next slide as well. But basically, that's the so-called Rabi oscillation. When it will be Rabi, a true Rabi, when you're at resonance, because then omega r will basically be lambda x, which is the amplitude of the driving, which is the same, that you guys that happens in many other contexts. So I wanted to show this as well here, because of course it's our work. It's first a student of mine back then. He's now moved to risk management at some big bank in Brazil, so he's probably making good money. And at that time, we investigated this work by the group of Joshua folk that many of you know, and that is Frolov. In the early days, Sergey. So At that time, he was a postdoc with Joshua Folk at UBC, and they were looking at wires that you'd spin inject here via QPC, and then the simple picture is that the electrons would just bounce back and forth here, and that of course you have an external field here applied in plane, and this bouncing would generate some kind of what they called ballistic spin resonance in this nice Nature paper here. And the explanation they had was basically using the spin-orbit interaction in the wire. So the spin-orbit interaction, say, of the Rajba and Dressel house, which is the case here, because it's if I'm not mistaken, it was gallium arsenide. You have both of them. One is much larger than the other, but it doesn't matter. So when you have a spin-orbit interaction, you can always write it as a Zeeman term. That's how you actually define your spin-orbit field. So for holes, it's going to be similar. It's much more complicated because you have to use the Luttinger cone Hamiltonian 4x4 because you have valence electrons, but the concept is the same. So for electrons, it's much simpler. For the Dressel house and the Rajba, because you were in 2-dag, and so the B field in 2-dag would be like this, right? So you can see here that the spin-orbit field, it has components along the X direction, this one, which is along the wire, and components along the Y direction. So, and of course, the components depend on the momentum of the electron that is basically going back and forth here along the Y direction. So as it moves up and down, the momentum, Py, changes sign. That means that this acts as an oscillating field along this direction here. And that's going to give you the resonance that we want. So there's an external field, and just like the previous picture, I'm now shaking it this way, but not via an external source, by just the bouncing back and forth, right, as it's shown here. So we generate an initial component that will give her some resonance. If you vary here, you vary the magnetic field to find the resonance. You find the external magnetic field. In the usual picture, you vary the frequency of the external drive, right? So this one, you can control that, of course, but it's much harder because you have to apply a gate to vary alpha. So at that time, they measured this. This is an experimental result. And if you just do a simple, as they had done in this paper here, basically equating the Zeeman field with the spin-orbit field to find the resonance, you'd find just one peak, one dip, because the whole experiment goes like, whenever you reach resonance, you dephase, and this thing would just go down here, because we can discuss this later, but the detector, the detection here will correlate the spin that you inject with the spin that is being measured here, and when it's in resonance, you basically depolarize the whole thing. So you'd see the dip, but they ended up seeing actually a plateau here, which was hard to explain, and then we did this simple calculation, quantizing the system because it's a wire, and then we found very good agreement. We can, so this is, so that's the idea of the Rabi oscillation of the, that we have. It's also the same for the holes. Now let's go back to this system now. So now I have, the simple model is I have the usual transverse driving, and because the spin orbit vector in this system has other components, you also have something that's like this here. And of course, our experimental colleagues, they can vary, they have a all-wave generator, they can add, oscillations at different frequencies and pump the system. So this is the Hamiltonian we have, and you can do the dynamic. It's very simple. Even I can do this, numerically. With Maple, for instance, I played a lot with that. Those figures that I showed you with the traces, I've done it. My son, I have to admit, did help me with getting the traces because it's tricky with Maple. But the main idea, the way the experiment is done, and this is how we all know, right? You start, say, with spin up, and then you shake it laterally, and this thing will eventually go down, and you can calculate all the probabilities. After some time, you ask yourself, what's the probability for the system to stay in the up state, for instance, or in the down state, or the probability for it to flip? And because the readout in this kind of experiment, it's a double dot geometry, as I showed you in that picture. So even though we're looking at just one qubit, but the readout involves the electron tunneling to the other dot and out. And for that, you use Pauli blocking, to do that. So because, a singlet has a different symmetry than the triplets. I don't want to get too much into details of that, but so this allows you to measure something by measuring the current. So in the simulation, what we basically have to calculate is this, quantity here. So you do it fully numerically if you want, and then you can get, all ranges. But of course, it's there's also some analytical developments, and for that, I'll briefly introduce this, which is very important, I think. So we all know Schrödinger's equation, time-dependent Schrödinger equation, and it's very simple to show that if you perform a unitary transformation, which is half, within half a page you can do that, you end up with this kind of Hamiltonian. Very simple. There's nothing really. So it looks like the original Hamiltonian, but now with an H tilde here, which is given by that, right? So that's very generic. There's nothing special there. And the trick is to choose U so that you end up within some approximation, or if you're lucky, exactly this Hamiltonian here, this new time-dependent Schrödinger equation may be separable in time. Maybe you end up with a Hamiltonian that is not time-dependent. That's the whole trick that you have to play when you do this rotating wave approximation. So you start with this Hamiltonian. That's the one I showed you. Going back to just one drive here for simplicity, you do this transformation. In this case, the U is chosen to be like this, which is basically a rotation around the z-axis. And so this Hamiltonian becomes this one here, where we define what we call detuning to be delta. So you end up with a two-level system now, and we still have the time dependence there. So it's actually worse. It looks uglier than this one. Well, now is when you do the rotating wave approximation, which is you basically expand the cosine here, and you multiply it out. So you get the 2 omega I omega x here and there. And then you argue that this is like fast oscillations. You drop them, and you end up with the Hamiltonian, which is now time dependent, that we all know how to solve. So, and then you can easily calculate the probability. That's how you do it. The formula I showed you before, it's here, right? I'm going through this in detail because I'm going to do exactly the same thing when I have the Don-Schuden drive. It's going to be more complicated, but it's basically the same idea. And then, of course, we now have the full story here, right? So you start with a fully time-dependent system. You do this transformation, and then you end up with something that, after you do the approximation, the rotating wave approximation, you end up with something that is time-independent that we all know how to solve. That's basically what it is. So if you plot those things, with numbers that are actually from the actual devices. You find the usual Rabi chevron, and when I started this business, they say this is a chevron. This chevron. I had no idea what a chevron was, so I would dig it out, and it's actually some pattern of tiling for floor, right? So that's what it is there. So it's just to check whether, I mean, this is numerical result. I'm just checking my little code here. So the numerical results and the analytical result, they all look nice. So nothing new here. So now let's see, when you do the phase drive, and I'm going to show the details, that chevron with the phase drive, it looks like this. I mean, I'm varying now. I mean, this is, I can take a cut from this other plot, and I can plot, say, it's a grayscale here, right? The probability times the the ratio, omega z and omega q here. So you get this kind of picture. I don't want really to discuss this much, but I can go into the details later if you want. And they actually measure this kind of pattern experimentally. And I was amazed, by the similarity, but I think the nicer one is this one. So we define z to be just the ratio. Let's see, where did I find it? Yeah, this ratio here. So lambda z is the intensity of the drive, the longitudinal drive, and that's the frequency of the longitudinal drive. So you vary from 0. That's basically saying that there is no longitudinal drive. You get your usual Rabi chevron, and then you start increasing this, and then you start seeing the appearance of sidebands, and then for this particular value here, z equals 1.2, you basically remove the main peak, and there's a reason for that. This 1.2 here turns out to be half of the value of the first root of a Bessel function, J0. So I'm going to show you this now. So in principle, so this is simulations, of course, but then they went into the lab and they measure that. So it's kind of very neat, in my opinion, the kind of things you can do. So experiment, theory. So you have basically a bunch of sidebands here. That's also showed in the paper as a nice way to control your qubit, generate additional sidebands in a controllable way by just varying a gate, which controls the intensity of the longitudinal drive. So again, we can do the same story, but now it's more complicated. So this is the kind of unitary transformation you have to consider. And then you do basically what I did. This was done before in some other paper by Bosco. And then you use this, one of those, equalities that we all learned somewhere, or at some point, maybe. So you can express that Hamiltonian, complicated, like this. So far, there has been no approximation, but you can see that this, if I single out n equals 0, 1, and use this property here, I can write my original rotating wave approximation. Yeah, I actually already did the rotating wave approximation for the transverse part. That's why I end up with this part here. But this, what was constant before, it's still constant, but now I have J0 modulating the transverse drive. And of course, and then you have all these other terms here. And what I mentioned before is that if you choose lambda z over omega z to be 1.2, then it will give you 2.4, which is a 0 of it's a root, it's a 0 of the Bessel function. Then you basically kill the main Rabi. So it's a way of renormalizing the Rabi. I mean, and in the first picture I showed you, you can also slow down also the Rabi, because if it's not exactly this value, you're basically modulating your Rabi drive, the transverse Rabi drive. So now what do you do with this? Well, this other part, as I showed before, with the transverse drive you do that, but then you can do the same thing for this other part. So as a first approximation, you just throw everything away, and that would explain this very first picture I showed you that I didn't want to discuss, because we vary lambda z over omega, right? So we basically showed that the Rabi drive frequency is changing. Or not the Rabi oscillation is changing because of omega 0. So this is what I was just saying, right? So this basically renormalizes that you're writing this in the spin language, which I call Spanish, not Spanish. You get the same stuff. So now you basically renormalize everything. This is just to show that how the peak, the main peak, disappears, right? But what about the other peaks? So then you have to basically do the same thing, same rotating wave approximation, but for the higher harmonics, right? And then we introduce this kind of parameter here, which could be, because you see this part here. So for the sake of simplicity, I'm sitting now at the 0 of the Bessel function. So this first term was gone, but then there are the other terms, right? So for the other terms, I do the rotating wave approximation. And by the way, here are the several values of this ratio here, for which you would get zeros on those for those Bessel functions. So same story. Let's focus, say, for instance, on this one here, right? Forget about this for a second. You would do the same thing for that. So this is basically what I had before. I'll do the rotating wave again. Same story, right? As I showed you before for the transverse drive. It's here. So if I just follow the analogy, comparing the two, I see that my detuning now is given by that, and this lambda bar here, which lambda x bar is now this, and I have same story as before, but for each of these harmonics, with the main peak gone because I chose already this value here, right? So this kind of this actually explains the positions. Okay, you can go on, and I'm just going to stop because I wanted to just point out this the idea that you have you can have this modulation. You can basically suppress the main peak and have sidebands, but you can play with that. I played a lot of it because there's some asymmetry in that chevron. If you look at it carefully, you see that the upper part and the lower part is not quite the same, but then you can write it like this, the Hamiltonian, and then you solve it numerically. And it's possible to trace the asymmetry in that modified chevron to the way keep adding the several harmonics of the Bessel functions. Yeah. So this is the asymmetry I was talking about. So then you play a lot with that. So I just wanted to show you this because it may be interesting. And the question is, because some of you and Dennis also mentioned that yesterday, is it possible to come up with something like this in the kind of system that you guys are interested, especially the ones that Dennis mentioned yesterday. At the March meeting, someone, I think it was Alex Hamilton, when I think when one of the experimentalists, I think Simon, was giving a talk, because he gave talks there, in 2023, and he shouted from the back, "Is this possible? Does it work for NMR?" And I think the idea is completely general. If you have, I think, any system that you have transverse drive and longitudinal drive. I mean, of course, in NMR, the frequency scales are different because, I didn't point this out here, but we're talking about gigahertz and megahertz for the longitudinal drive, megahertz, and the transverse drive is in the gigahertz regime. And of course, for NMR, you'd have something like kilohertz and megahertz, if I'm not completely offside. So, but in principle, I think it should be possible to have it there. Of course, there are many other issues concerning, I don't know, the coherence, spin flip, whatever, right? But so that's what I wanted to tell you. Thank you for your attention. So, if you have any question, Dennis, I'm getting that's my role here. All right.
Thank you very much, Carlos. Very interesting. Two-tone physics. So you mentioned that here you're using holes for realizing this, and the whole like RF driving field comes from the spin orbit. For the electron spin half, I understand the cosine of diagonal and the cosine on the diagonal because it's sigma z, sigma x. But for the whole qubits where you have cubic spin orbit term, wouldn't we get something like cosine cubed of like a frequency or like something around those lines? I'm just like trying to understand how to go.
What I said is, so this Hamiltonian that I'm using, a model Hamiltonian, it can actually be justified if you start with the Luttinger cone Hamiltonian, and then you confine it to make a dot. And then, of course, you have to include all the couplings, light hole, heavy hole coupling, and you end up, after massaging this a lot, you end up with a 2x2 Hamiltonian for kind of pseudo spin for holes, but of course it has this, it's coupled to the light holes, right? And with the field, which is actually 3D, the spin orbit field. That's very different than, say, for electrons in zinc plane, which you get in linear order. Both the Dresselhaus and the Rajba are in plane, right? And that's how you get, for instance, the persistent spin helix. But I think even we haven't thought about this for electrons. For instance, with the cubic, even for electrons with the cubic Dresselhaus, you actually have components out of plane. And in principle, it could be applied there as well. But I haven't done anything on that. For the holes, it's just natural. It's just complicated. If you search literature, you won't really find anyone writing down this spin orbit field in a generic way, right? You can just write sort of the very generic Hamiltonian with all these different components. And certainly there will be a transverse and a longitudinal. But for instance, for this Wurtzite system, that could be an interesting thing, because you saw I showed you in this very, one of the first few slides, where we have a very complicated spin orbit coupling, which has components, even for electrons in many different directions. So,
just a follow-up question. Thank you for the answer. Is there any? Because when I think about this like Rabi oscillations, we're thinking about like single qubit gates. Mm-hmm. So, does this present any advantage over just like controlling the Rabi frequency? And the other question is, can we use somehow these like sidebands for, I don't know, qubits or any?
Yeah. So if you check our paper, and towards the end we discuss it's this part where you have the BS part of the paper where you talk about possible. PRL allows you to have paragraph fantasize. So yeah, we say exactly that. This buses where you can. I'm not an experimentalist, but of course my colleagues wrote that. I think when you doing processing, it's better to do it at megahertz frequencies as opposed, or smaller frequencies as opposed to. I think it has to do with the packing, of wiring and all that. So this is one thing. And the other question was, I forgot.
It was just, I mean, for instance, why is it better to use two-tone microwave instead of just one microwave that's that you can like adjust and change?
Well, I think for the zero of the Bessel function, you need to you have to have that ratio that in this picture here, it's lambda z over omega z, and I think I don't think you can get this if they're both. Well, naturally, you know, we can certainly discuss this later, but naturally, when you write down this Hamiltonian, which is in principle derivable from the Luttinger cone, these frequencies are already. I mean, of course, you can always use gigahertz in both, but then you would not be able to get this kind of result. So this mismatch is important. You know, it's like a 1K mismatch. You know, 1,000 times larger, right? So we have gigahertz and megahertz here. Yeah. Okay, now I'm going to have to really understand the accent here.
Oh, I'll try and talk really slowly. So, I mean, of course, with a magnon, you can't do Rabi flopping because it's linear, right? But another two sort of commenty things is, one is that when you're trying to work out what's happening with decoherence and spins and optical transitions in rare earths, the ability to do echoes gives you lots and lots of information, right? Because you can do different pulse sequences and different timescales and all that sort of stuff. And the other thing about spin echoes and photon echoes, especially just the two pulse ones, you hit any old two pulses in and you'll always get an echo out, right? As long as they're sort of big enough, right? So you're not sensitive to the size of the pulses too much. Mm-hmm. Do you think there's any possibility of using the nonlinearity that are there in magnons to do something like an echo?
So in this paper, we actually say that the advantage of that is that we don't really need nonlinearities to get this harmonics, right? But of course, I think there are papers in the literature in this business in which the nonlinearity will give you, additional things. Not exactly like that, but harmonics. I actually don't know. I was actually motivated by Dennis's talk yesterday, where he mentioned that he has this transverse qubit and longitudinal qubit, and sort of, we talked briefly yesterday, and apparently there is some kind of mapping, but we still have to figure out. I don't know. Maybe, we have to discuss together. Yeah.
You said that you have a megahertz and a gigahertz fields, but my question is, like, how far those two fields need to be in order for you to be able to apply this theory? For example, if the mismatch between the frequency of the, like, what is the gap between the two fields, or the minimum gap between them that you need to have in order for this theory to be valid?
So those are the numbers we have, right? So the qubit frequency is like 5 gigahertz, and then omega z, it depends. Here it's 0, so there's no. And here lambda z, the first one here, lambda z, which is the intensity of the drive, and this is the frequency of the longitudinal drive. So if this is 0, there's no drive, right? But then we increase it, and also the frequency, because we want to look at this ratio here. So for this ratio equals 0.3, you start to decrease this because of this J0, and you start seeing the side bands, and then right at this point here, like when lambda z and omega z, the ratio gives you 1.2, that you hit the 0, then you basically kill this main peak, and then you have the side bands. So those are roughly the numbers, experimental numbers. Those are experimental numbers, even though there's theory, but this is exactly what was used for the, in the experiments to generate, here, those are the numbers that we use. So this is the frequency difference, and I think different samples, I mean, they have others. Actually, this is the second sample that was measured over Christmas back then in 2023, because the previous version, the previous frequency that had, the previous samples that they had sort of died, and it was really great that Simon managed to do this for a new sample. But so the numbers change, but you always, in principle, should be able to find this. I'm not sure if you're worried about how different the frequencies have to be.
Yeah, the one along Z and the one along X, like the longitude and the...
Yeah, so this is the ratios that we have. Yeah. Hans?
It's maybe a super technical question. So when people, so in more generalized spin resonance experiments with Rabi spectroscopy, people also look at these chevron papers, but from time to time they depict it as function of the output. They do a Fourier transform along the time axis and then look at the frequency spectrum which comes about in order to identify coupling to nuclear spins or to other electronic spins, and I think you can certainly do this here, and this might be illustrative for the coupling rates or the induced coupling rates that you have as an external control knob. So did you do this? And is it then easy to identify the frequencies and the drive amplitudes that you plug in from the outside? For
this system, yes, because the theory came first. So we it's interesting because it's very neat, So we at that time could tell the experiment, so you should look in this range. I was really surprised when we saw this first picture. That so there has to be some guidance from the theory, and for and it's amazing because this is a mass. So, this is not a single qubit, whole qubit. I mean, God knows how many we have there, but there's probably one unpaired. And of course, we have also some additional work that one of my students is involved in. Bill is also involved. That's they measure different things like quantum capacitance and things like that. And the theory does not really match. And Bill has this nice idea that maybe you're looking at a larger spin ground state, some kind of instability like ferromagnetic. Let's not call it ferromagnetic because it's a finite system, but and that generates additional splitting. So I don't think it's for this kind of system, it's complicated. There's also the issues of coherence time. These are not electrons in gallium arsenide or a nice system. That's a whole this, and the spin-orbit interaction has this dual role that it allows you to probe the system. You have a knob to shake things, but at the same time, it couples your qubit to charge noise and kind of thing. But on this point, I wanted to say that there's a nice. I didn't have time to show that, but we can. This is like towards the end of the paper. This longitudinal drive, if you look at the Hamiltonian, right? It's basically to make a connection with some of the words used earlier on. It actually, you can connect this to flocate states. Because think about it, have your qubit, and you're now shaking it longitudinally, periodically. So there's going to be a sort of Bloch's theorem, and it was Ivan who did that, right? Who showed that. So here, and one of the points in my conclusion, I say that depending on this ratio here, it's possible to find, if you plot now the band structure like Ivan showed, and this is stroboscopic band structure, because it's a flow case state, you open up gaps. Just like the nearly free electron model of solid state physics, right? You have your free electron, now you turn on your lattice weakly, and then because of the Bragg reflection, you open up a gap. So kind of the same thing happened here in the spectrum. So you open up a gap somewhere in the spectrum, that sort of protects you a little bit with respect to noise, simply because you're gapping out your spectrum. So yeah, but yeah, so there, this basically, I don't think people are, a lot of these students finished, some of them are leaving, and I'm not sure whether this, I mean, we have other things that I was involved in, and it's in the back burner for some time now, especially involving the 2 qubit part, right, where there's a J interaction. There's all very interesting things. Yeah. All right. So thank you very much. Sorry for my 9 minutes over. So I guess we can go for lunch now. Huh?